Human beings are understanding machines. And because of that, we have attitudes and we have assumptions that we bring to the world around us. Well, science is an understanding machine, and it's no different. So today we're going to take a look at the attitudes and assumptions that are incorporated into the scientific process. Hello, my name is Dr. Igor Juricevic, and this is Functional Analysis of Behavior 1. Let's go. So today we're going to talk one more time about the scientific method. Remember, we're zooming out, talking about science, so we can understand applied behavior analysis, so we can understand functional analysis of behavior. This is going to be the last one where we take a look at science specifically. And today we're going to take a look at the attitudes and assumptions of science to see what this entire endeavor is built upon. So the assumptions and attitudes of science that we're going to take a look at today are determinism, empiricism, experimentation, replication, parsimony, and philosophic doubt. Science is all about discovering the laws of the universe. How do things actually operate? And if we're going to discover something, we got to assume that it exists. So if we thought that there were no laws out there, we wouldn't even bother trying to discover them. So one of the first assumptions of science is determinism. The universe is a lawful and orderly place, and then our job as scientists becomes to discover those laws to impose our own order on this universe. Next is an attitude of science, and this is empiricism. And empiricism is the objective observation of the phenomenon of interest. And if you recall from previous videos, for us, the phenomenon of interest is socially important behaviors. But objective observation means that when we observe the world, when we observe things like socially important behaviors, we make these observations independent of what we believe, of what we think, of what we bring ourselves to the table. So what this really means is that two people with completely different beliefs should observe the same event as being the same if they're observing it objectively. So we don't impose our own order, our own subjective experience onto the world. We try to be objective and observe it without beliefs, without biases, as much as possible, without introducing our own ideas into the things that we observe. Now, experimentation we touched on in the previous video. It is the specific manipulation of one event, that is the independent variable or the cause, to determine if it produces a reliable specific change in another event, that is the dependent variable or the effect, when you control for extraneous factors, and those are the confounding variables. So again, we're manipulating something, the cause, to see if something else changes, the effect, and we're making sure that nothing else can be causing that change, that is the extraneous variables. Now, what an experiment does is it allows you to establish a connection between the cause and the effect, or as we like to call it here, a functional relation. A functional relation between one event that causes another event. And for functional analysis of behavior, these functional relations are very important. This is what functional analysis is all about. So one aspect or one meaning of the term functional analysis is the demonstration of these functional relations between environmental variables, things that we can control, and behaviors, things that we're hoping to affect. Another way that functional analysis, the term is used in functional analysis of behavior, is to refer to the specific experimental methodology for determining these environmental variables and the contingencies maintaining that problem behavior. So in one way, functional analysis is the demonstration of those functional relations. And the other sense of the term is that functional analysis is the discovery of those relations between environmental variables and behaviors. So an example of a functional analysis, a controlled experiment where we manipulated one independent variable to see if it caused an effect on the dependent variable, comes from, I'm going to try to pronounce that name, Iwata, Dorsey, Slipher, Bauman, and Richmond study toward a functional analysis of self-injury. So what they did in this study basically was they put different subjects into different conditions and then measured their rates of self-injury. So they specifically manipulated the conditions, and then they saw what effect that manipulation of the environment or the conditions had on the rates of self-control. So to show you what a functional relation looks like, let's take a look at child number 1 there. And basically on that line, the height of the line indicates the rates of self-abuse. So the higher the line, the higher the rate of self-injury. And then the different types of lines are the different conditions that they had them in. And we'll call them academic, alone, social disapproval, and play. And what we can see here is that there is a functional relation between the type of environment or the type of condition and rates of self-injury. So that the rate of self-injury was the highest in the academic setting and low in alone, social disapproval, and play settings. What that means is that we now have control. We have a functional relation where if we want to reduce the amount of self-injurious behavior in child number 1, we would manipulate the condition that they're in. We would take them out of that academic condition and put them in any of those other 3 conditions, and thereby we could control the amount of self-injurious behavior. All right, the next attitude we're going to take a look at is replication. So what replication is, it's repeating experiments to demonstrate reliability and the usefulness of finding. So what replication is repeating experiments to determine the reliability and usefulness of findings. So what replication is all right, enough of that. So when you find a potential functional relationship in the experiment, there's always the possibility that that is a chance event, that we really didn't find a real, true functional relationship. We just saw the covariation of 2 variables and we mistook it for a functional relationship. And the best way to determine which of those scenarios is true is through replication. Do the experiment again, and if the functional relationship keeps appearing, then the chances that it's due to random factors goes way down, and we're more confident that we have a reliable functional relation. So the next attitude and assumption of science that we're going to take a look at is parsimony. And parsimony is our preference as scientists for simple logical explanations before we move on to more complex or abstract explanations. We look for the simplest explanations for the phenomenon before we take a look at more complicated, more out there, more kind of like crazy, wacko explanations. So that's parsimony, our preference for those simple explanations. If everything is equal, so if the simple explanation is as good as a complex explanation, we're going to prefer the simple explanation. And this has actually popped up in a number of different places. So for example, we've seen it in the famous adage from Sherlock Holmes that when you have eliminated all which is impossible, then whatever remains, however improbable, must be the truth. And another way of saying this is you want to eliminate every single easy, simple explanation. Eliminate those first. And then whatever you have left over, however crazy, wacky it might be, that has to be the truth. But notice you don't start off with the crazy, wacky possibility. You start off with the simple ones and eliminate those first. This is also reflected in the Occam's razor principle of science. So Occam's razor basically states that when you're given an explanation, you do not want to multiply entities without necessity. So you don't want to start having to come up with new ideas, new formulations, if they're not absolutely necessary. You want to keep it as simple as possible before you start exploding with the number of concepts that you need for an explanation. And a nice real world example of this comes from Dr. Thomas Woodhouse and his famous quote, "When you hear hoofbeats, think of horses, not zebras." So this was advice given to medical students to help them in their diagnoses. And again, this is a nice example of Occam's razor, because let's say that you were on a farm and you heard hoofbeats. It's a very simple theory to attribute those to horses. So you're on a farm, farms have horses, therefore those hoofbeats are probably a horse. A more crazy explanation that would still account for the hoofbeats would be that the hoofbeats come from zebras. But notice what you need to do. You need to add multiple levels of explanation to that, because you're on a farm in the United States. How did a zebra get there? Well, then you'd have to add stuff like maybe your zebra escaped from the zoo. Well, how did a zebra escape from the zoo? Maybe there was a gap in the bars. Well, why was there a gap in the bars? Maybe the manufacturer didn't follow safety protocols. Well, why didn't the manufacturer follow safety protocols? And on and on and on. You would need a very expanded theory that starts going off in all wild and crazy directions, and that violates that idea of parsimony. So it's a horse, very simple. It's a zebra, super complex. We as scientists prefer to go with the horse explanation. Now, that's not saying that it's never going to be zebras, but our first step is to take a look at the simple theories before we start taking a look at the super complex theories. All right, and our last attitude of science is philosophic doubt. And this is the idea that as much as we want to get to the truth of what is out there, as much as science is about discovering the truth of the universe, we are always open to the idea that we might be wrong. And that is one of the hard lessons to learn in science. And thankfully, my PhD supervisor, Dr. John Kennedy, was one of, I would say, the world's leaders in this idea, because he once told me that as a scientist, you actually want to be wrong, but you want to be wrong first. And what that means is that you want to make contributions, you want to pursue knowledge, you want to drive forth this search for truth, but always have it in the back of the mind that what you find might be wrong. It might not be true. And we as scientists do our best. We accept what other people have done, and we accept the research as being our best guess to the truth, but we don't hold it up in some holy temple of truth as unassailable knowledge. We know that as we continue to learn, as we continue to grow, what we once thought was our best answer might turn out to be completely wrong, and new answers are required. All right, so that wraps up our video today. So again, we looked at the attitudes and assumptions of science. We took a look at determinism, empiricism, experimentation, replication, parsimony, and we finished it all off with philosophic doubt. So thank you so much for joining me today. Be sure to come back next time when we start taking a look at the concepts and principles in applied behavior analysis. So now we're going to drill back down into specifically applied behavior analysis and start to take a look at the specific concepts and ideas that we need for functional analysis of behavior. So until then, thank you for joining me. Stay frosty, stay functional, and I'll see you next time. Now, experimentation we touched on in the previous video. It is the